Good evening, all. This is Jayashree Nair. So today I will take VBT theory of coordination compounds. This is very interesting theory. With examples, I will explain. So the chapter name is coordination compounds, and this is VBT theory. What is VBT? VBT means valence bond theory. And what is the importance of this valence bond theory? So far, before valence bond theory, we have studied about Werner's theory. But Werner's theory couldn't explain the magnetic properties and the directional properties of the complex compounds. That is why VBT is formulated. So using VBT, we can predict the hybridization, the structure, and the magnetic properties of the complex compounds. So with examples, we will see first. Let us take the example, the CO coordination, this coordination number, that is CO NH3 6 times 3 plus. So I hope all of you have the basics to find out the oxidation number of central metal atom. That is central metal atom here is cobalt, right? And ammonia is a ligand here, and the ligand ammonia is neutral. That is, it's a compound. So oxidation number will be 0. So this CO and the total oxidation number of the coordination entity is 3 plus. So the cobalt's oxidation number will be 3 plus. So 3 plus plus 0 equal to 3 plus. This is how we are finding out the oxidation number of the central metal atom here. Now we have to write in a systematic way, we will write and see the valence bond theory of this complex. So cobalt, first we have to write the atomic number of cobalt is 27. So the electronic configuration, that is a valence electronic configuration, will be 4s2 3d7. It is easy to understand, children, not at all difficult. Like if the atomic number is 27, for the valence electronic configuration will be 4s2 3d7. If it is 28, 4s2 3d8, like that. Now cobalt is 4s2 3d7, but here it is cobalt 3 plus. We have to find out the electronic configuration of cobalt 3 plus. That means 3 electrons will be removed. So which 3 electrons will be removed? First, these 2 electrons will be removed, and then 1 electron from this 7 will be removed. So we will get 4s0 3d6. This is the electronic configuration of cobalt 3 plus. Right. Now we will draw the orbital configuration. How we will write? See, 3d6. According to Hund's rule of maximum multiplicity, this 3D configuration I will write like this. I am going to show the electrons. The first electron, second electron, third, fourth, fifth. And the sixth electron will get paired up here, right? This is the way we will, according to the Hund's rule of multiplicity, we will arrange the electrons. Then next we have 4s orbital and 4p orbital also. This is 4s and this is 4p. You should understand that cobalt is coming in fourth period. Cobalt coming in fourth period. Fourth period means there will be 3D orbital, 4 is 4p and 4d also. I am not writing 4d right now because it is not needed here. Now, next is ammonia. We have to consider the ligand ammonia. Ammonia is a strong ligand. The end of the class, I will give the chart of which all the ligands are strong and which all the ligands are weak. Okay, so now you understand that ammonia is a strong ligand. A strong ligand can pair up the electron of the central metal atom. So you have to write ammonia. CnH3 is a strong ligand. Strong ligand which can pair up the electrons of the central metal atom. That means this electrons will be paired up. You can see that central metal atom electrons will be paired up. Then again I will write in presence of ammonia. I will write the orbital configuration once again. So I should understand that the electrons will get paired up. That means this electron will go here and this electron will go here. So I can write the paired up configuration like this. Okay, now we have 4s and we have 4p. Now you know that in cobalt, around cobalt, 6 ammonias are there. That means the coordination number of cobalt is 6. That means 6 ammonia will give electrons to cobalt. So cobalt should be able to accept the 6 electron in 6 hybridized orbital. In order to get 6 hybridized orbital, there should be 6 individual orbital. Which are the 6 individual orbital? We will see. 1, 2, 3, 4, 5, 6. This is of 3D and this is 4s and this is 4p. That means there will be an hybridization between these 6 orbitals. So that what will you get? You will get 6 hybridized orbital. And what is the name of this hybridization? You can see that d orbit. How many d orbitals are there? 2 d orbitals, 1 s orbital and 3 p orbital. So we can understand that the hybridization will be D2sp3 hybridization. So hybridization is D2sp3. This is the first thing we have to find out. Now, next is the spatial arrangement or geometry. Whenever there is 6 is the coordination number, there can be there should be the spatial arrangement should be octahedral. So I can write here shape. Shape will be octahedral. I hope all of you know the octahedral shape. Otherwise, I will show it here. That means if 6 ligands are around cobalt, so cobalt will be in the center and 6 ammonia will be in the corners of a square and one on the top, one on the bottom. So that the shape will be like this. These are bonds and these dots are all ammonia. So 6 ammonias are arranged around cobalt in the shape of an octahedral. Octahedral shape is otherwise known as square bipyramidal also. You can see that this is a square and there will be two pyramidals on the top and bottom. That is a shape. See, this is a pyramid on the top and one pyramid on the bottom also. So this is the shape of the octahedral of this complex, that is cobalt and 6 ammonia around the cobalt. Okay, so we have studied about the hybridization, how to find out the hybridization and how to find out the shape also. Now next question is whether this complex is inner orbital or outer orbital. You can see that 3D orbitals are utilized for the hybridization. That is, it is inside. 3D is inside, outside is fourth shell. And 3D, you know that 3 is coming inner to 4. So because 3D is utilized, not 4D. We are not using 4D, we are using 3D. And 3D is inside, so that it is an inner orbital. Inner orbital. The complex is inner orbital. Now, next question is magnetic character. Magnetic character. What is a magnetic character? You know that there are two types of elements or complexes, that is paramagnets or diamagnet. Diamagnet means not at all magnetic. Paramagnetic means very weakly magnetic. Clear? And what is the criteria for this? There should be unpaired electrons to be paramagnetic. If unpaired electrons are there only, the complex is paramagnetic. If all the electrons are paired, then the complex is diamagnetic. Now you can see that all the electrons here are paired. Clear? And here this hybridized orbital electrons will come from ammonia that will be already paired. I will draw it and show also. So you can see that all the electrons are paired. If all the electrons are paired, it will be, the complex will be diamagnetic. Fine. Now it's all over. All the characteristic which is coming in VBT theory, which we can understand by VBT theory, I have explained here. Now, little more in detail, I would like to explain this, how the complex is formed. That means, here you can see that the orbital configuration is 3D, 1 minute, 3D, 4S, and 4P. So I'm showing it together. That is a hybridized one I'm showing together. So these are 3D where electrons are already present, and this is 6 hybridized orbitals. That is what hybridization here? D2sp3. 6 hybridized orbitals are there, right? So now we know that electrons are already there. That is, these 3 electrons are already there. Now you should understand that 6 ammonia are around cobalt. This 3D and D2sp3 configuration is of cobalts. Okay, now around cobalt, 6 ammonia are there, and this 6 ammonia will give electrons to cobalt, and cobalt will accept the electron in this empty orbital. So there is a bond formation where both the electrons are contributed by ammonia. So this is known as coordination bond. That is why these complexes are known as coordination complex. Like this. So this here also, you can see that here also pair of electrons will come. Cobalt could accept this many electrons because cobalt is present in D block. It's a transition element. So surely it will have empty d orbital. That is why coordination compounds are mainly formed by transition elements. So you can understand why coordination compounds are mainly formed by transition element. What is the reason? The reason is that transition element have empty d orbitals to accept the electron from the ligands. And by VBT theory, we can understand the hybridization. And by VBT theory, we can understand the shape and whether the complex is inner orbital or outer orbital and the magnetic character of the complex. I hope you understood this example. So I have explained an example which is sp3d2, that is coordination number 6 I have explained. Now one more hybridization is possible in coordination number 6 that we will see. That will come when the ligand is weak. Now we have seen an example with ligand very strong, right? Now we will see an example with ligand weak. Next example. Example 2, the coordination compound. What coordination compound? Here we will take, see, cobalt F6. We will take this coordination compound, that is cobalt F6 3 minus. So as I said, what is our first work in this? What should be done? Immediately when you get a complex, what should be done? See, we have to find out the oxidation number of cobalt. What is the oxidation number of cobalt here? See, total oxidation number. We know total oxidation number is 3 minus. I will tell you how to find out the oxidation number of the central metal atom. Suppose this is the oxidation number of cobalt is X. F is 1 minus we know. So minus 1 into 6 is equal to minus 6. The total should be minus 3. So X plus minus 6 is equal to minus 3. So X is equal to minus 3 plus 6 is equal to plus 3. So cobalt here is plus 3. The oxidation number of cobalt is plus 3. That you should understand and find out first. Okay. Now next information here I will give you. F is a weak ligand which cannot pair up the electrons of the central metal atom. Very, very important point. F is a weak ligand which cannot pair up the electrons of the central metal atom. Then we will again find out cobalt 3. Cobalt 3, we will find out the 3 plus, we will find out the electronic configuration. This is 27. 3 electrons are gone. So I have already shown that it is 4s0, 3d, 6. Now we will draw the electronic orbital configuration. This is all we have. I am again repeating actually. 1, 2, 3, 4, 5, 6. This is 3D. Then we have 4S and we have 4P. And remember, as I told, because it is in the fourth period, 4D also is possible. This is 4D. Of course, these are empty, but it is there. Orbitals are present there. Now, next is, as I said, F is a weak ligand. It cannot pair up the electrons in 3D orbital of the cobalt. So, orbital pairing up will not take place. And we know here also the coordination number is 6. 6 means 6 empty orbital should be there. That means 6 empty orbital should hybridize to form a hybridized orbitals. So one is this, 1, 2, 3, 4, 5, 6. These are the 6 orbital which will get hybridized. So what you will get? sp3d2. So the hybridization is sp3d2. This is the hybridization now. It is slightly different from the hybridization what we have studied. So now once again I will draw this. These are the electrons present here. And now 6 orbitals will be the which is hybridized. sp3d2 and the rest 3 orbital which is coming in 4d. I am talking about this orbital, children, which is not useful here. Okay, I have written here. And the middle, the 6 orbitals are sp3d2 hybridized. Okay, so to which sp3d2 orbitals and sp3d2 hybridized orbital to which fluorine will donate electrons by, and there will be a bond formation which is coordinate bond formation. Now let us see the hybridization. I will write down all the points here. Hybridization first. We know the hybridization is sp3d2. Now shape. Of course, 3 fluorines are around the cobalt. So as I said before, it will be octahedral only. So you can understand one thing. If the coordination number is 6, there can be 2 types of hybridization, D2sp3 and sp3d2. In both the cases, shape will be octahedral. Now we will write inner or outer orbital. You know that for the hybridization we are using outer d orbital, that is 4d orbital. So this is an outer orbital. Outer orbital complex. Then next is magnetic character. Now you can guess what is a magnetic character. How can we see the magnetic character? We will see whether there are unpaired electrons are present or not. That is magnetic character. So you can see that there are enough unpaired electrons. See, 4 unpaired electrons are there. So of course this is paramagnetic. So we have seen all the things. We have seen the hybridization. We have seen the shape and outer or inner orbital and the magnetic character. So I'm teaching you, in this video, I'm teaching you only octahedral. That is only coordination number 6. Okay. Next video, we will see the VBT theory with coordination number 4 also. Thank you, children. Thank you for listening.